Welcome to the very first lecture of Spring Quarter Math 200. In this lecture, we're going to introduce the concept and language of sets. So set theory is a very well-developed branch of mathematics that's very important and basically serves as a very foundational topic and subject for a lot of mathematics. So what is a set, you ask? Well, the definition is quite simple, but there's some important subtleties that we'll have to consider. Here's the definition. A set is any well-defined theoretical collection of objects. So let's unpack this definition, starting with what we mean by objects. Despite how it may sound at first, objects does not refer to physical things. It is a general term that certainly can refer to physical things, but also any sort of noun. So even abstract things like numbers or colors or ideas or words or anything like that. Next, sets are theoretical collections in that even if we are talking about a collection of physical things, we don't need to actually possess the collection. Really, we only need to be able to conceive of it or think about it. This implies that there is even a set containing the planet Mars and the color purple. It's just a theoretical collection. Finally, sets must be well defined, meaning that we should definitely be able to tell whether or not something belongs to the set. Let's consider a few cases, and we'll start by considering things that are not sets because they're not well defined. Is there a set of really big numbers? If you think about that, the answer has to be no, since it's not clear at all what would count as being really big. What about the set of all beautiful paintings? Is that a set? Again, the answer has to be no, because what counts as being a beautiful painting is completely subjective. Let's contrast these with things like the set of all numbers greater than 1 million and the set of all paintings currently hanging in a museum. These are actually well-defined sets because there's no question as to what does or does not belong to the set, at least in principle. Now for our first bit of terminology. We refer to the objects in a set as the set's elements. When we wish to specify a set, we need a way of indicating what elements belong to the set. This leads us to the notation we use to specify sets. The first notation is called roster notation and is the most obvious way to specify a set, namely just list out all the elements. We do this within curly brackets. So for example, the set of all digits can be expressed as, in curly brackets, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The strength of this notation is in how straightforward it is, but if you think about it, it has an obvious drawback. It's really only feasible for small sets or sets that have a nice pattern. What I mean by that is if you consider something like the set of all natural numbers, which is infinitely large, it still has a noticeable pattern that we can use. So we could still use roster notation for this set by writing something like, in curly brackets, 1, 2, 3, 4, dot, dot, dot. That ellipsis or the dot, dot, dot means and so on. And that's something we can get away with since we can see what the pattern is by listing the first few numbers, which really means we can get to any of the other elements by just adding 1 every time. Many sets are just too large though, and there's no usable pattern. In fact, the elements may not be listable even in principle. In those cases, we need a different kind of notation that will allow us to handle things like that. And this is where our second notation, which is called set builder notation, comes in. It works by picking out the desired elements by describing some kind of a property they all satisfy or share in common. Now, while this notation is more powerful, it's also a bit more abstract and requires the use of some variables. Let's write out what the format looks like first. So when we use set builder notation, here's what the format will look like. We still use curly brackets, and the first part, we have some kind of a variable expression, and we separate that by a bar, and on the other side, we list the condition or property that has to be satisfied. So let's look at a few examples. Our first example is one that cannot be put in roster notation, even in principle. It's totally impossible. This is the set of all real numbers from 0 to 1, which is actually an interval. It's a chunk of the real number line. In set builder notation, we would specify this as this. We read this as the set of all x such that x is greater than or equal to 0, but less than or equal to 1. Now our variable expression is just x, and the property or condition to be satisfied is that x can only represent a number that is greater than or equal to 0, but has to be less than or equal to 1. Here's another example. Consider the set of all rational numbers. In set builder, we express this as the set of all things of the form n over d, such that n and d are integers, and d is not allowed to be 0. Since rational numbers are just fractions, our variable expression is a ratio of two variables showing that structure, the n over d. The condition is that the variables can only be integers, with the one exception that d is not allowed to be 0 because we are actually never allowed to divide by 0. One last example. We could even have something like the set of all f such that f is my friend on Facebook. Now, once we have specified a set using either type of notation, whether it's roster or set builder notation, we generally like to give it a name, usually some kind of a capital letter. That way it's easy to reference later whenever we need to. For instance, we might name or label the set of all digits by D. The set of all rational numbers actually has an agreed upon label, which is just a fancy Q that looks like this. Now, since sets consist of elements, we need a way of saying whether something belongs to the set or not. For example, consider the statement 3 is an element of the set D, where D, of course, is the set of digits from earlier. In set theory, we have a symbol that represents the relation is an element of. It looks like a fancy E, like this. So in set language, we write 3 element of D. And if we want to say something like 11 is not in the set D, we write this. In other words, we put a dash through the symbol. I should also point out that we will often see things like X element of D, where X is a variable. Now we should not take this literally as saying that the letter X is in the set D. Instead, when we use a variable, we are saying that the variable, which in this case is X, represents something from the set D. Now let's revisit the set of all friends I have on Facebook. Some of those friends are also family members, and I can think of these people as forming their own set, namely the set of all family members that are my Facebook friends. Let's label the set of all Facebook friends by F, and let's let the set of family members who are my Facebook friends, let's call that R. Clearly R and F are related, since every element of R is also an element of F. In other words, if someone is a Facebook friend that is a family member, then clearly they are also a Facebook friend. We say that the set R is a subset of the set F, since R is just a collection of things from F. And we notate this subset relationship as this. You can read this as saying R is a subset of F, or equivalently as R is contained in F. The little underbar allows for the possibility that sets R and F are equal. That is, maybe my friends list consists of only family members. Now for a quick side note, this brings up an issue we should stop and consider just a little more carefully, namely, what does it mean for two sets to be equal? For example, are any of the following sets equal? Since sets are just collections, they have no structure. So what does this entail? It entails that two sets are equal if and only if they are coextensive, which is just a fancy way of saying that they contain all the same elements. We can also phrase this in terms of the subsets we were just talking about. Two sets, let's call them A and B, are equal if and only if A is a subset of B and B is a subset of A. In light of this, we can see that sets 1, 3, and 4 are all equal. 1 and 3 are equal because they clearly have all the same numbers listed, even though they're not in the same order. So what we see is that order doesn't matter. Sets 1 and 3 are also equal to set 4 because the numbers 1, 2, 3, 4, and 5 are all natural numbers that satisfy the given inequality. Set 2 is actually an infinitely large set of numbers consisting of all possible real numbers from 1 to 5, so it cannot be equal to the others. All right, with that said, let's talk a little bit more about subsets. A set can have many different subsets, and the bigger the set is, the more subsets it has. For example, let's consider something that's actually a bit small so we don't overwhelm ourselves. Consider the set A is the collection of A, B, and C. The set of all subsets of A is actually a set, and we call it the power set of A. And it's sometimes denoted like this. Again, this is the collection of all subsets of the set A. And in this case, we have this collection. Now, the first thing to notice is that there is an empty set of brackets in there. Why is that? This is a special set known as the empty set. It is the set with no elements. So it's kind of like an empty container. It actually has an established label, which looks like this. Okay, but how is it a subset, you might ask? Well, let's consider the statement that the empty set is a subset of A. A statement like this is either true or it's false. But if we think about it, what would make such a statement false? Now, if we remember back, if we say something like S1 is a subset of S2, that means that every element of S1 is also an element of S2. So really the only way for the statement that the empty set is a subset of A to be false is if the empty set has an element that is not in A. But of course the empty set has no elements. So this isn't possible, and thus there is no way for the statement empty set is a subset of A to be false. So by default then, it's got to be a true statement. So that may seem a bit counterintuitive at first, but what we need to remember is that the empty set is always a subset of any set whatsoever. So any set we write down, the empty set will always be considered one of the possible subsets. The other subset that might seem slightly counterintuitive is the whole set itself, namely in this case, the set ABC. It seems awkward to say that the entire set is a subset of itself, but it does count. If you think about it, it trivially satisfies the definition. Everything that's in the set A, B, and C is also an element of the set A, B, and C. We call this an improper subset. All other subsets are called proper subsets. We can even make a fun little diagram showing the subset structure of all these sets. It looks like this. So now we know what sets are to some extent and some important concepts and notation involved. So that'll do it for this lecture. In the next lecture, we'll discuss how sets have their own algebra. So that will be fun. So we will see you there.